This video is going to cover moment area method. Now, it's definitely my least favorite method, but it does work and it does get everything to the same answer as any other method would. The difficulty honestly comes from getting your moment diagram correctly. If you get your moment diagram correct, everything's easy. Now, you don't have to do method of superposition if you don't enjoy method of superposition, but superposition for the moment diagram is supposed to make things go quicker for you. However, if you take the wrong end as your fixed end for the method of superposition, this method can turn out to not be quite as fun. So just keep that in mind. So for this example, we're going to find the slope at D and the deflection at A for the given beam. So first up, we have our deflected shape. So here's our deflected shape, and we need to start doing some really fun geometry to figure out what we actually need to calculate. So we need to start finding some tangents. So we're going to have the tangent at C here. So this line is going to be the tangent at C. Then we also need at point D, who is roughly in the middle here, we're also going to need the tangent at D. So he's about right here. And again, that's going to be the tangent at D. So what we were asked to find is angle of D. So angle of D is going to be, he's going to be real small in here. But angle of D is going to be that guy right there. Might be best to move him into a different spot. So we're gonna stick him down below. That's angle of D. So in order to find the angle of D, we have to use a little bit of geometry. So what we're gonna do is, one of our moment area theorems is that the angle between two tangents, specifically this one here, is going to be the angle of tangent C with respect to tangent D is going to be the sum of the area on the moment diagram between those 2 points, so between C and D. So that's great, but that really doesn't do much for us. So we need a little bit more information in order to finish figuring out what we have here. So this line here is our horizontal, and so is the line that the arrow is pointing to for angle D. So this one is angle of C. So what I can tell is going on here is that we have angle of C is equal to angle of C with respect to D plus angle D. If we write it in just a little bit different way, we have that angle of D is equal to the angle of C minus the angle of C with respect to D. So this is going to be the way that we want to try and find angle of D. So that's what we want to solve for. How do we find, we know how to find angle of C with respect to D, but how do you find angle C? Well, angle C, we know that the distance between these 2 points is 4 meters and 4 meters, so that's a total of 8 meters. And if we knew the height of the triangle that we're creating here, then we could easily find that information through trig. So the height here is what we want to find. Now this is the vertical deviation of point B, that's the roller down here, with respect to the tangent C. That's how we do it. We go from the point on the elastic curve, that's point B, to the tangent at C. That's the vertical deviation of point B with respect to C. Now our moment area theorem says that the vertical deviation of one point to another is going to be the moment of the moment diagram, the area of the moment diagram taken about the first letter, so taken about point B. So that's how we're going to find angle of D. So let's go ahead and write this out. So we said angle of C is equal to, it's going to be the tangent, but remember all slope and deflection, it's all small angle theory. So small angle theory says you can honestly just drop the tangent part of it, and it's just going to be equal to the opposite, which is the vertical deviation of B with respect to C, over the adjacent, which is 8 meters. So we have two things we have to calculate. We have to calculate the slope of C with respect to D, and we have to find the vertical deviation of B with respect to C. So step number one, we now need our moment diagram. So the biggest thing is to pick what point we actually want to fix. And I'm going to give you a hint. We actually want to fix at B. The reason we want to fix at B is because it's going to give us a very, very easy diagram for moment. So this is our moment diagram, positive, negative. What we're going to do is we need to find, we don't actually need BY. What we do need is CY. And don't forget, over here, we had an 18 kilonewton force. So just looking at our basic free body diagram, what we're going to do is we're going to sum the forces, sum the moments, can't sum the forces. We're going to sum the moments about B. I'm going to take counterclockwise to be positive. We're going to set it equal to 0. So we have 18 kilonewtons times 3 meters. That's going to be going positively around B. And then CY is also going to go positive. So we have plus CY times his distance of 8 meters. So CY is going to equal negative 6.75 kilonewtons. So coming down here, again, remember we have negative 6.75 kilonewtons. So we're going to be doing the method of superposition, assuming that we are fixing at B. That's why I drew that line here vertically. So on our left side here, we're going to start at 0, where that point is taken at, and then it's going to go linearly. Right? Linearly, it's going to go down to P times L. Why P times L? P times L is the moment. That's where that came from, in case you're wondering. So 18 times 3 is actually going to be 54. And we are going down, so it is negative 54. Now, we're going to do the same thing. Of course, we're not going to look at anything on B, because BY doesn't create a moment about B, by the way. So next, we're going to do CY. And CY, we drew it up, but remember, he's actually negative. So he's going to be negative 6.75 times 8, which, go figure, that's going to balance out this equation right here. So that's going to give you the same exact value. So we're going to be going from 0, and again, I know that arrow's drawn up, but technically, CY is technically down 6.75. That's what our negative sign here means. Don't mess that up. So, negative 54. That is our diagram with superposition. Pretty easy, actually, and if you were to do the shear diagram for this beam and the moment diagram for this beam, you're going to get the exact same diagram. So again, really doesn't matter, but superposition is supposed to make this easier. So now that we have our moment diagram, what we need to do is find theta of C with respect to D. So again, that's going to be the area between C and D. So the area between C and D, we probably need to note where D is. And D is probably not right there. Oop. Well, D is going to be probably about right here. That's probably D. Remember, he's 4 meters in from each end. So close enough. So we need to find the area between C. C is over here. This is B, and way over here is A, just to mark those out. So we need to find the area between C and D. That's this piece right there. So we're going to use some similar triangles here. And we've got a distance of 8 meters and a height of 54. And we're going to go a distance of 4 meters, and I want to find height y. So 54 over 8 is equal to y over 4. So that's going to be 1/2 of 54. So y is equal to, I didn't do the math, but anyway, it's 1/2 of 54. So what we're going to do now is find the area under the curve. So the slope of C with respect to D is equal to, it's a triangle, so that's 1/2. The base is 4, and we said the height was, it's going to be 4 over 8 times 54. By the way, it's negative. Let's go put that negative out in the front so he doesn't look awkward. Ta-da! So what this is going to equal is, this is half, and then this is times 2, so it's actually negative 54, funny enough. So the angle of C with respect to D is negative 54. Now again, this is all kilonewton meters squared over EI, which again, you can carry that stuff with you if you want, or you can just leave it off till the very end. I'm not going to cry if you do. So we have angle of C with respect to D. Next on our list, we need the vertical deviation of B with respect to C. So the vertical deviation of B with respect to C is going to equal the moment of the area of B to C, this area right here, taken about B. Okay, taken about B. So we have 1/2 times the base of 8 meters times the height of negative 54 times his distance from the centroid, which is about right here, to B. So that's going to be 1/3 of the total distance of 8. And that's going to give us negative 576. Again, if you want to put your units, it's kilonewtons, meters cubed over EI, technically. So then what do we need to do? We need to divide by 8 to get our slope at C. So slope at C is equal to the vertical deviation of B with respect to C over 8 meters. So negative 576 divided by 8 gives us negative 72. Again, we divided by 8 meters, by the way, so that's going to be, again, kilonewton meters squared over EI, if you really want to keep up with it. So we wanted to find angle of D. So angle of D is equal to angle of C minus angle of C with respect to D. So what we really wanted was angle of D is equal to the angle of C minus 72 minus the angle of C with respect to D, which was minus 54. So that's going to all turn positive, and we're going to be left with negative 18. Again, kilonewtons meters squared over EI. Ta-da. That's how simple this is supposed to be when your moment diagram is not very complex. Next up, the hard part. How do you find the deflection at A? And remember, A is all the way over here. So how do we find the deflection? Well, for starters, what can we do? We can calculate the vertical deviation here, and this is going to be the vertical deviation of point A with respect to the purple line is tangent at C. Okay, so that gets us the total, but I don't want the total. What I really want is this distance from here down. That is actually the deflection at A. So if I could say get rid of this part, we're going to call this H. How would we do that? Well, that's a similar triangle. This is 3 more meters of this wonderful triangle that tangent of C is creating than the vertical deviation of B with respect to C. So we got some similar triangles going. So if I want to say write out that the deflection of A is going to equal the vertical deviation of A with respect to C minus H. And H we need to find by similar triangles. So we can draw it out. Right, we have H on the end here. It's 11 total meters. It's 8 plus 3. Then on the inside, we have 8 meters. And this is the vertical deviation of B with respect to C. So writing it out, H over 11 is equal to the vertical deviation of B with respect to C over 8. So H is equal to vertical deviation of B with respect to C times 11 over 8. Ta-da! Well, good news is we've already got the vertical deviation of B with respect to C. So we already find what H is. Now we just need the vertical deviation of A with respect to C. So back here on our diagram, we need to find the vertical deviation of A with respect to C. So we need the area of all the stuff between A and C, all of that taken about A. So that's going to get fun. Those triangles, not as fun. So the vertical deviation of A with respect to C, we have the moment of the area under the curve. So we have 1/2, we're going to go again left to right. We have 1/2. The base of the first one is 3 meters. So 1/2 times 3 meters times the height, -54, times the distance from his centroid, which is right here, over to A. So that's going to be 2/3 the overall base of 3. Plus, we have the area from B to C, which is 1/2 the base of 8, the height of -54, and the distance from his centroid over was 1/3 of 8 plus the whole distance of 3, right? Because we're going to go 1/3 of 8 to get to B, and then we got to go from B all the way over to A. So, again, we have -54, -54. So this is going to be a negative value. We have the vertical deviation of A with respect to C. We're going to get -1,386. This is technically kilonewton meters cubed over EI. Super fun, right? And again, we want to find H. So H is equal to, we found that guy to be -576. So -576 times 11 over 8. H is going to turn out to be -792. And we said, looking way back up at this, that the deflection at A is the tangent, or the vertical deviation from A to C minus H. So we have the deflection of A is equal to the vertical deviation of A with respect to C, so minus 1386 minus H, and H is -792. Those add together there, and we're going to get -594 kilonewtons meters cubed over EI. So, in all honesty, this problem does not seem very difficult when you think about it, but it can be quite difficult if you do the wrong moment diagram. So, for instance, I can tell you about all of the things that really were horrible for me in making this video. Was I originally started and I fixed C, and then you have one triangle going down, and then you have BY going up, so then you have two different triangles, and you're doing a whole bunch of more triangle math than you should have to. So if it's easier to just do the shear diagram first, and then the moment diagram just the old way that we normally do, just so that you have a very simple moment diagram, you can do that as well. So the big key thing is going to be this moment diagram looking as simple as humanly possible. So the less areas you have to find, the less moments you have to find, the less likely you are to eventually screw up this problem.